There we go. Hola, Coimbra. Eu sou Dave Aronson, o T-Rex de Codosaurus, e vou para cá para no pterodátilo desta missão para vos ensinar sobre algoritmos genéticos, mas vou fazê-lo em inglês. So, what are genetic algorithms in the first place? The category as a whole is an optimization meta-heuristic, meaning that each genetic algorithm is an optimization heuristic, which is fancy talk for the idea that the category as a whole is a category of shortcuts to find a good enough solution to some problem, usually something that would be computationally intractable by traditional means like brute force or precise calculation. Ideally, this will get us the best answer, but we'll usually have to settle for something just good enough due to constraints like time and money. There are lots of kinds of optimization heuristics, but genetic algorithms are unlike most of the others in that they are inspired by real-world biological evolution, mostly the principles of survival of the fittest, combination of old sets of genes, no, not like the ones I'm wearing, into a new set, and random mutation. The history goes back to about 1950, when Alan Turing, as in Turing machine, Turing completeness, Turing award, Turing test, and all kinds of other Turing stuff, proposed a learning machine in which he thought that the mechanism of learning would turn out to be somewhat similar to evolution. Nothing much ever really came of that. And it took a few decades before genetic algorithms as a whole got any serious traction. Then the first commercial product based on genetic algorithms, a mainframe toolkit for industrial processes, came out in the late 1980s from General Electric. In 1989, a more generalized toolkit running on PCs came out called Evolver. These days, MATLAB and other such tools usually have genetic algorithm facilities built in, and there are genetic algorithm libraries available for most major programming languages. In fact, someone just showed me one for Java over the lunch break. However, the actual uses of genetic algorithms still remains mostly rather obscure, not very publicly visible, and honestly, at least in my opinion, a little boring. They're used mostly for things like company internal scheduling and logistics, and of course still industrial processes and such applications. But once in a while, they do get used for something a little more interesting and more publicly visible. Most famously in 2005, NASA, the United States National Aeronautics and Space Administration, used a genetic algorithm to design the antenna for its ST-5 series of satellites, which they then launched in 2006. No, that's not just a bent-up paperclip that got bent up by somebody fidgeting in a boring meeting. The NASA Jet Propulsion Laboratory website says, "Its unusual shape is expected because most human antenna designers would never think of such a design." And that's actually one of the great advantages of this approach. These algorithms are not so hampered by expectations of any similarity to past solutions, what an antenna should look like. They can come up with things that a human would never think of, but the numbers work out fine, so okay, they went with it. But today, we'll only be looking at much simpler problem domains, mainly for the purpose of making an understandable demo. So how do genetic algorithms work? They consist of a series of 5 simple steps, plus an initial 6th one. First, we create a population of candidates, or in genetic algorithms terms, they're called chromosomes. But since every living being contains lots and lots of chromosomes in each of lots and lots of cells, I never liked that term. I think it just leads to confusion. So I just call them candidates. I've also heard them called individuals or solutions or phenotypes, if you want to use another actual genetic term. But most people don't know that word either, so I skipped that one too. The next step is to assess how fit each of these new candidates are, according to whatever criteria we want to apply. And we do this step mainly because it supplies the information needed for the next step, which is to ask, are we there yet? Or are we done doing the whole cycle, which I'll complete in a moment? This is usually based on the fitness. It could be based on some other criteria, and we'll discuss some of those later on. If we're not done, then we select some of the candidates to use in breeding the next population, and then of course we use the ones we just selected to actually breed the next set of candidates. Some of the previous population, especially the most fit, might be carried over into this new population, but usually not. And next is a very important but easily forgotten step, which is to mutate them, which gets you more diversity in the gene pool. And finally, we go back to step 2, assessing how fit each of these candidates are, now that we've created a new population and mutated them. You might want to take a picture of this slide and the next one, because between them, they're kind of the main takeaways about how genetic algorithms work at a very high level. I don't see anybody rushing to take out their phones. Don't worry, the last slide includes the URL for all the slides, so you don't really need to. Okay, I see one. I'll give you a moment. Okay. Now, this sequence of events could be represented at a very high level in code like this. Now, I know this conference tends to focus a lot on Java and JavaScript, hence the J in JNation, but this is actually Ruby, which I chose because it reads very close to plain English. So even if you don't know Ruby, I'm pretty sure you'll understand at least the concept, if not, and probably rather, the actual code. Now let's take a closer look at what happens at each of these steps by walking through some examples. First, we create an initial population of candidates, but what is a candidate and how do we create one? These are different solutions to some problem, usually represented by different instances of the same data structure. And this could be any data structure we want, so long as we can evaluate how fit these solutions are for our purpose, combine 2, or maybe more, old ones into a new one, and somehow mutate them. The simplest common type of candidate is a simple string of bits. And this will do fine for situations where your solution is a series of yes-no decisions. And that may sound simplistic, but there's actually a huge category of problems that boil down to this. You may have heard of knapsack problems. This is a subcategory of constrained resource allocation problems, if you want to get a little more formal. The canonical example is that you have a knapsack, or rucksack, or backpack, whatever you call it, and you have a bunch of items that you want to carry in it, but they won't all fit. Or maybe they total up to more weight than you can carry, or some other such constraint, or possibly combination of constraints. And you want to get the combination that will fit the constraints and has the maximum value. Now, this could be the literal cash value, or it could be something more metaphorical. In the usual illustration, you have a knapsack that you're taking on a camping trip. So, of course, you want to take those things that are going to contribute the most to your comfort or possibly even survival. For instance, common camping supplies would be much more valuable than, say, an accordion. To look at a more concrete example, let's suppose we know a farmer who has a smallish truck, and he needs to decide what to take to market every week. And on this farm, he has some cows. E-I-E-I-O. So among the things he can take to market are cows, milk, cheese, butter, ice cream, meat, and leather. My apologies to any vegetarians and vegans out there. For the sake of simplicity, we won't differentiate between price and profit or between meat and dairy cows. And even though it's rather unrealistic, we'll assume he always has some particular set amount of it on hand and can only take that amount. Now, his truck actually has room to take everything, but it can only handle 4,000 pounds, in other words, 2 tons. Don't get me started on our stupid American units. So that's going to be our constraint. His choices are as follows. You don't need to really pay much attention to anything but this total down here of 8,600 pounds, which would be a little over 4 tons, almost a little over 4 1/4. Now, we could brute force the entire solution space, going through all the combinations and seeing which of the ones that is light enough for the truck has the highest value. Or we could use another common heuristic specifically for knapsack problems of always taking the most valuable item that will still fit within our constraints. But let's see what happens if we use a genetic algorithm. First, we need a way to represent each truckload. And in code, that could look like this. You might think, well, that looks like we're just making a random number. Yes, we're making a random number with 7 bits. So we have a random 1 or 0 for each one of the possible items we could take. We could get as complex as we want in this function, like dictating a minimum or maximum number of different products, but I'm going to just keep it simple. To create an initial population, we could just create a bunch of these and stuff them into an array like so. And for those of you who actually do know Ruby, yes, this could be done in much more idiomatic Ruby. I'm just trying to keep it understandable for those who don't. So we create an initial population of 10 truckloads, which could wind up with something like this. Now, why 10? Because that's what fits on the screen at a decently readable size. If I were doing this for real with a more complex domain, I might use 100, 1,000, 1,000,000, whatever might be appropriate. But how do we get from those random numbers to these combinations? Behind the scenes, that translation might look like this. We have the list of items we can take, each represented as an instance of a class describing them with name, weight, and value attributes. In this example, it's an inner class, but it doesn't have to be. To check what's in our cargo manifest, we can just iterate over the items we could possibly take and see if the corresponding bit is on. But I'll just hand wave over those details to keep things simple. Anyway, now that we're done with the initialization step and we have our truckloads, we assess how fit each of these truckloads is. And we do this with what's called a fitness function. Surprise! Just how biological creatures might be a perfect fit for one particular ecological niche, but a horrible fit for another. A fitness function should reflect the fitness for whatever application we have at hand. In this instance, we know he's taking the stuff to market, so we want the just plain cash value. But any truckload that is too heavy for the truck is actually worthless, so that gets knocked down to 0. And in Ruby, that could look like this. We decode which items we want to take, sum up their weights, and Again, writing the bit on function is left as an exercise to keep this code simple. And if those weights total more than the capacity of the truck, then that truckload is worthless, so we return 0. Otherwise, we use a similar technique to sum up their values. And again, we could get as complex as we want in this function, and NASA's antenna fitness function certainly must have been. But for instance, if the truck were even smaller so that the volume mattered more, we could take the volume of each item into account. We could even take into account the exact actual dimensions so that he wants to take perhaps a flagpole. The total volume and weight might be rather small, but its actual length might be too much to actually fit in the truck. Now, if we run this fitness function on our current population of truckloads and sort on the fitness descending just to make it easy to find the best one, we wind up with this. And you don't have to pay much attention to anything but the top one, the best truckload we have, is worth $20,000. So now that we've assessed how fit these truckloads are, we can ask, are we done yet? So what are our criteria for that? This function can be very simple, but it can take a lot of thinking to figure out exactly what it should do for best results. And you'll find that with some of the other functions as well. With a knapsack problem, a very good solution, and especially the very best solution, can be made absolutely worthless by adding just one more wafer-thin item and thereby exceeding the constraints. So what we're going to do is hold on to the best one we've seen and just try to outdo it. We'll stop if we haven't seen anything better within 100 generations. Why 100? Pretty much random. It seems like enough for a good possibility for improvement. And since what we're doing is rather simple and the population is rather small, that's not going to take much time. In Ruby, that would look like this. When this code is initially parsed to define the function, we set the best combination as empty and the number of generations since we've seen it as 0, both as class variables. That's what the double @ signs mean. When the function is called, we increment the number of generations, look at the fitness of the current population, select the ones with a better fitness than our current benchmark. If there are any, there may well not be, we make the fittest one the new benchmark and reset our generation counter. Otherwise, we'll look at how many generations it's been since we saw the best one. If it's over 100, well, actually over or equal to, yeah, whatever, it's kind of hard to read there. Anyway, if it's reached the number of generations we want to let it go, then, well, that's our definition of done. So we return true, otherwise we return false. As usual, we could get as complicated as we want in this function. Not only looking at the maximum fitness, we could also check the average or the minimum, and we could look at completely unrelated stopping criteria, like some number of generations in total or some amount of time, whether wall clock time or CPU time, or even let the user click a stop button or any combination of those and others. Since we're not done in this particular case, the next step is to select some breeders to breed the next generation. The obvious way is to take the top 2, like so. We take the populations, sort them, reverse them, so we have them in descending order, and just take the first 2. Out of our current population, that would get us these 2, our 20,001 and a fairly distant runner-up at 14,800. And there are a few other ways, actually many other ways, but a few other common ways to select the breeders. For instance, there's one called roulette wheel selection, in which they're chosen randomly, but each one has a chance to be chosen proportional to their fitness. So for instance, out of however many it totals up, this top one would have 20,000 chances to be selected, and that one would have 14,800 chances to be selected. You can think of it like being their number of tickets in a lottery. I think the roulette thing is a little misnamed. We could also take more than two, whether to breed all pairs in that set, or maybe even to combine more than two at one time. And we can combine these strategies, like selecting 5 by roulette and then breeding all trios within that, or any other sort of complication we want to apply. Now that we've chosen the breeders, the next step is to actually use them to breed the next population. And the usual way to do that is called crossover. This consists of taking the data points, or in genetic algorithm terms, the genes, hence the name, from one parent up to some randomly chosen crossover point, and then take them from the other parent. And this can be extended in various ways, like with multiple crossover points going back and forth, but we're just going to use one, like so. We establish the crossover point for a particular candidate as a random number between 0 and however many items there are inclusive. Then we go through the list of items one by one, and if we've hit the crossover point yet, then we take the decision from the second parent, else we get it from the first parent. And this could yield results anywhere from 0 from the first parent and all from the second to the other way around. And as usual, we could get as complicated as we want here, like making some crossover points more likely than others and various other complications. If we do this once with a crossover point of 3, so we get 3 values from the first and the rest from the other, that could get us a result like this. But this is just one of 10 results because we're making a whole new population. And the code to do that could be like this. You might notice that this is very similar to how we created the initial population. However, now, instead of each candidate being made from scratch, they're the result of breeding the 2 chosen breeders. And the whole list might look like this. One particular aspect of this really jumps out, and that's that there is quite a lot of family resemblance. None of these loads include a cow, or butter, or leather, and they all include cheese. And that's because both of our breeders were like that. If we were to just continue breeding the best of each generation, we wouldn't ever see any truckloads, including a cow, butter, leather, or no cheese. But we fix that in the next step, which is to mutate them. And again, I'm going to keep it very simple and just give each gene a 1 in 4 chance of flipping. And in code, that might look like this. We iterate through the item numbers, and for each one, if a random number from 0 to 3 is a 0, gotta love those off by 1 errors. Yeah. Anyway, if a random number from 0 to 3 is a 0, we flip that bit. And again, we could get as complicated as we want in here, like having some genes more likely to mutate than others, or having a minimum or maximum number of mutations per candidate, or all kinds of other options. If we run this mutation function on our current population, we might wind up with something like this, where the green color means that that bit flipped. You can see that we now do have some loads that include a cow, butter, leather, or no cheese. Now we go back to step 2 and assess how fit this new population is now that we've mutated them so they're in their more or less final state. And that would get us this chart. Oh no! Our maximum fitness actually went down. You may recall our previous best one was 20,000. But don't worry, as you might remember from the "are we done yet" function, we just hold on to the best one and try to outdo it, so we haven't lost it, no problem. However, this isn't really the best approach. Remember how I said that sometimes the fittest members of the previous population might be carried over to the new population? If I had done that, the maximum fitness would never go down because we always have the one from the previous population. So the are we done function could be much simpler and we'd be done sooner. But I didn't think of that until after I'd already done all the slides for this talk and I didn't want to change them. Also, I think this version is still worth exploring to show how the maximum fitness can go down and come back up later. So you're not necessarily stuck on a local maximum. Anyway, the next generation might look like this. And you might notice that now we're back up not only to, but over 20,000. So we have a slight improvement over our original best truckload. So we set that top one as our new benchmark, reset the generation counter, and keep going. And if we let this run to completion, no, I'm not going to bother with each and every generation, much to your relief, we might wind up with something like this. So we wind up with 26,000 with a truckload made of cheese, meat, and leather. So that's one complete run of a genetic algorithm. And if we wanted to be sure that this was the best that this algorithm could produce, we could just run it again. And again, however many times we want within reason. Because in the general case, it's so much faster than brute force or, in some equations, very precise calculation. Now, in this example, maybe writing all that code and running this multiple times might not be faster than brute force. But if we were dealing with more items for more truckloads per week, maybe per day, and more complex criteria, then yes, writing a genetic algorithm may well be worthwhile. Now suppose we want to evolve something completely different. Suppose we want to evolve a good set of statistics for a Dungeons & Dragons fighter character. So now our candidates are tuples, or if you prefer, tuples, of numbers rather than strings of bits. Dungeons & Dragons character statistics are strength, intelligence, dexterity, constitution, wisdom, and charisma, each one made up by rolling 3 six-sided dice, or 3d6, as we at least used to say back in the day when I played Dungeons & Dragons. And I will ignore how you could have extra strength sometimes. I'm just going to make that little simplification to the rules. Now, in Ruby, creating such a character might look like this. And again, defining a function, in this case roll, is left as an exercise just to keep this code simple. So if we create an initial population of 10 characters, that might look like this. Pretty fair to middling characters. Now that's the initialization step done with, so next we assess how fit each of these characters is. And we're trying to evolve a set of fighter stats, so these should be based mostly on the strength and constitution and a bit of dexterity. The intelligence and wisdom and charisma, not so much. But we don't want them too low because of occasional saving throws. I tried several different things, such as totaling up double the strength, plus the constitution, plus half the dexterity, but the other stats started to get too low, and even the dexterity was suffering. So then I tried prioritizing them linearly, adding up 6 times the strength, 5 times the constitution, and so on down to 1 times the charisma. But then the other stats started to get too high, and the characters were more generalized. So I finally settled on prioritizing them more exponentially, totaling up 32 times the strength, 16 times the constitution, and so on down to 1 times the charisma. So the upshot of that is that even though these functions can be very simple, it can be rather difficult to figure out exactly what they should really do for best results, whatever best results means for the situation at hand. And if we run this on our current population and sort them, we get this. So we have a range of 476 up to 760. Now that we have their fitness, we can ask, are we done yet? But again, what are our criteria? Let's say we're done if any candidate gets 90% of the way to the maximum score of our fitness function. I'll spare you most of the math, but the maximum is 1,134, so 90% would round to 1,021. And in code, checking that would look like this. Very simple. None of our current candidates score anywhere near 1,021, so of course we're not done. So now we select a couple of breeders to breed the next generation, and I'm going to stick with the technique of taking the top two most fit. Taking the top two, we get these two. And now the abstraction gets a little more obviously leaky because we're ignoring sexes. That's not even part of the data. We have no guarantee that these two characters will be a male and a female. So we had the same leak last time, but that was not so relevant. The truckloads weren't living beings, so I let it slide. Now that we're dealing with living, even if imaginary beings, whether they're humans or elves or whatever, it could become relevant. It could complicate our breeding function or our breeder selection function enormously, possibly even making it impossible to find a viable pair in such a small population. But fortunately, for the purposes of this demo, we can ignore that. So next we actually use these two breeders to breed the next population. And this time we'll use a slightly different strategy of essentially flipping a coin for each gene. Like so. We go through the stats one by one, and for each one we flip a coin, or as I said way back when, we roll a D2. And if that comes up a 1, we get the stat from the first parent, else we get it from the other parent. And that might get us a result like this. But again, this is just one of 10 results because we're making a whole new population, which might look something like this. And there are two things to notice here. First, the number of red and green, which I'm using to denote coming from the first or second parent, is not always the same, neither in a single candidate nor in the whole population. It's a series of random coin flips, so on average there will be 3 and 3, but just like with the truckloads, it could be anything from 6 from one and 0 from the other to the other way around. Second, we still have quite a lot of family resemblance. Even though now we have 2 possible values for each column, not just 1, there's only 2, which is still a lot of family resemblance. In genetic algorithms terms, what we have here is 2 alleles for that given gene. And we would have only 1 allele for a particular gene if it were the same for both parents. That would also mean half as many potential combinations. Assuming that both parents were different in each stat, we would have 64 possible values. If one of those stats were the same between them, we'd only have 32, and so on down to the base case of 1. Now, at a glance, these do look much more suitable to be fighters than our previous population, but we'll figure their actual fitness a little later. Just like before, if we continued just breeding the best of this population, we'd never see any change, let alone improvement. For instance, the wisdom would never be anything other than a 6 or an 11. But we fix that in the next step, which is to mutate them. And as usual, I'm going to keep it very simple and just give each stat an equal chance of either staying the same or going up a point or going down a point, though clamped within the valid range. So in code, that could look like this. So for each stat, we basically add a random number from 0 to 2 and subtract 1, which is essentially like adding -1 to 1. But then we clamp it within the valid range. of 3 to 18. And as usual, we could get as complex as we want here, like giving it a higher chance of going up or coming down if it were already very low or very high to begin with, possibly even doing so by multiple points, or making some of these genes more likely to mutate than others. But as usual, I'm going to keep it simple. If we run this on our current population, we might wind up with this, where the green means it went up and red means it went down. Looks kind of like a Christmas tree up there. Now, looking at the values in each column, this highlighter isn't very bright, but you get the idea. Looking at the values in each column, you can see it's now much more diverse. So now we go back to step 2 and see how fit this new population is. And that would yield this result. Now we see that this new population is in fact much better suited to be fighters than the previous population. The old one ranged from 476 to 760, and now we're going from 635 up to 851. Significant improvement. But it's still nowhere near our stopping criterion of 1021. So fast forwarding through 6 more rounds, we finally get one suitable character with 18 strength and constitution, acceptable though subpar dexterity, that fitness function might still need a little bit of work, and surprisingly high intelligence. Now that's not a problem, but it is a bit of a waste. If we really wanted the characters more specialized, we could complicate the fitness function even more, to do something like explicitly demand that all of the class's useful stats, in this case the strength, dexterity, and constitution, all be well above average, and forbid it to be well above average for the other stats, or at least apply some sort of moderating penalty. So now we've evolved a set of fighter stats. Let's suppose we don't need any more fighters in the party, but now we want a wizard. All we need to do is to tweak our fitness function just a little bit, like so. Now we prioritize intelligence, then wisdom and dexterity, and so on down to strength, instead of almost the reverse. We could also make this take parameters and pass in a different ordering or something, but I'm just going to keep it hard-coded here for simplicity. Now, an initial population would look pretty much the same, since we haven't changed how that's generated. So I'll spare you those steps, but after 11 generations, I got this with 3 characters, at least 90% fit to be wizards. They're mostly pretty good in the other stats, but not so much as to be obviously better suited for some other character class, except that top one looks kind of like a bard to me. Remember, though, that this is all very random. It may converge on a good solution more quickly or more slowly, and the fitness function may be good or maybe poor at getting just the right mix of alleles so that they come out just how you want. There are many other ways of using genetic algorithms. They can create images, even code. I started working on one to make music, but couldn't figure out a good fitness function, how to evaluate how good a melody is. Oh well. I'm also working on one to create a schedule for a conference, given what talks there are and what they're about and so forth. And May Besaron has a talk about using it to schedule college classes and things like that. So just think about it, and you might be able to come up with some problem you're facing that you might be able to use a genetic algorithm for. To recap what you've learned here today, genetic algorithms are optimization heuristics, which is fancy talk for shortcuts to finding good enough solutions. They're simpler than you probably thought, and they can use very simple functions, but it can be difficult to figure out exactly what those functions should do for best results, whatever that means. They're also applicable to a huge variety of problems, including ones so complex that they can think of solutions that we humans would never have thought of. Now, if you have any questions, I'll take almost 10 minutes worth now. And later, there's my contact information up there. As for the other URLs, that first one is for the slides in HTML and some additional code. And the other one, as you may have guessed, is for the slides as a PDF, complete with a script, which I've mostly stuck to. So, any questions? Yes?
Is there any other way that having a crossover, like instead of choosing completely that gene from the parent, mixing genes? Or is that just solved by the mutation step next?
I'm not quite sure what you're trying to ask.
Instead of taking either strength from one parent or the other, averaging it out, or some combination of the genes?
Oh,
or do we just use the mutation to solve that?
okay. The question is there some way other than taking the gene from one parent or the other, just literally
Mixing the genes.
right, as opposed to doing something like averaging the two? Yes, you could certainly use that option. I've not seen that very often, but it's been occasionally suggested. Just as a wild guess, I would think it would probably lead more quickly to regression to the mean, but if you do that before the step of then mutating them so they could then go further away from mean, that might be perfectly viable. Okay, I see a hand for a question over there. Yeah, we have a mic runner.
So, do I understand correctly that for this to make sense, there should be a big number of parameters? Because I think correct cycle can be solved in square, and testing 100 options will be less efficient than dynamic solution.
I'm sorry, I didn't quite understand that.
I mean,
I can take a stab at what I think you might be
efficient.
asking. That does it matter whether if you have just like a few genes in each chromosome, or is it better when there is just a whole bunch of them, a huge number?
The type of problems then itself, they should contain many parameters to make this more efficient than precise solution.
Yes, there are some problems it's just not worth doing this for. If it's sufficiently simple, yeah, it might be, in fact, easier to just code up a brute force thing rather than a genetic algorithm. Like if we only had 7 things we could take to market or whatever. But if we had like, a much more complicated number of choices there, or each one was described by a much larger number of parameters. Like if we had, instead of just 6 character stats, we had like 1,000 of them. Maybe we're doing that huge number of dimensions for I forget what they call it, but for a large language model. Then yes, that would be much better of a candidate for a genetic algorithm. Basically, the worse it would be to brute force or do precise calculation in some physics things that require recursive refinement and so forth, then the better a candidate it is for shortcuts like a genetic algorithm. Does that answer what you're asking?
Yeah, thank you.
Okay, we have 1 minute left.
Yeah, he's very quick, so sorry. Regarding the
5, okay, never mind.
Sorry. The fitness function definition, there are any golden rule or approach that we can follow to define it? Because the way I understood your explanation is just by trial and error that we try to understand which will be the perfect fitness formula to compute it, let's say.
I do not know of a good heuristic to find the perfect fitness function. I suppose perhaps one could apply a genetic algorithm to create the code to do that. It seems to me like it would be highly variable from domain to domain.
Thank you.
I'll try and research that, maybe for the next version of this talk. Okay, we have 4.5 minutes left.
Hi. What do you think the fitness function for the NASA and antenna would look like? Because since it's a physical thing, how would they evaluate its fitness? Do you think they could somehow simulate it?
Okay, I am not an antenna designer, so I don't know for sure, but I would assume, keeping in mind what happens then, that there are ways one can take an antenna design and figure out things like how much power it needs to generate a signal of a given strength at a given distance away, or some such things. Or I would guess there are probably other parameters like how precise the frequencies get. Maybe there's some noise it generates or whatever. And if anybody out there is an antenna designer, you can tell this guy the parameters of an antenna. And presumably NASA figured out how to evaluate those assorted parameters in some kind of code.